Good morning, everyone. My name is Cam Mack from Lattice Semiconductor, and Andrew Canis from Lega Computing. We are going to be speaking today on the topic of software programmable FPGA on in IoT platform, and explain how do we use the RISC V processor and the leg-up high-level synthesis technology together in our product. To begin our presentation, this is the agenda of today. First, we will introduce our company and who we are. Then we will talk about the IoT platform in FPGA and how do we use the RISC V in our platform. Then I will hand over the presentation to Andrew. He will talk about the high-level synthesis tools and how is that going to work with the RISC V processor. And at the end, we'll have some benchmark result and a Q&A section. Lattice Semiconductor was founded in 1983, and we provide smart connectivity solution powered by our low-power FPGA, video ASSP, and other products to our customer worldwide. And our biggest commitment to our customer is to create an even better and more connecting world. And Lega Computing is a startup company, spin-off of 7 years of research at University of Toronto. They have created high-level synthesis tools that enable software engineering easily to compile the C language program into hardware on an FPGA. So, first of all, what is the vision of Lattice? So, when we start this project, we have two main goals we want to achieve. The first one is ease of use. Since nowadays, most of the embedded designers are using C or C++ as their design entry mechanism. And also, we want to create a way for the customer to create hardware accelerators using C language on the FPGA. So we want to put a RISC V plus a leg-up generator accelerators on our product. This way, we have a main advantage of not using any Verilog or VHDL in our product. And secondly, the flexibility. Since there's a lot of different type of IoT device in the market, we need to support a wide range of sensors, actuators, or communications devices. And we want also have the capability to generate custom solution, custom acceleration libraries on our product. So that's why we want an FPGA to fulfill this. So therefore, we come up with a hybrid solution that combines the RISC V processor plus the leg-up technology with our FPGA to utilize our low-power, small footprint FPGA for the user customization. So this chart here shows how we differentiate ourselves to our major competitors. So a hybrid platform processor plus a FPGA is not something new on the market. But our major competitors are selling their high-end FPGA to the data centers and cloud computing business. But Lattice is not playing in that spectrum. Instead, we are trying to selling our low-cost, low-power FPGA to the embedded, mobiles, and Internet of Things market. So basically, what is IoT? So IoT usually refers to a physical network of things that usually embedded with sensors, actuators, softwares, and allow these things to collect raw data informations like your smartwatch you're wearing or the smart electronics at your home. And usually this will connect to a local network like your home router, your smartphone, that tied to the internet. And usually, and such that the user can access and control these things remotely. And in some company, they will use this anonymous data from the user for their business data analysis, and marketing purpose. So basically, as I mentioned before, an IoT device can be usually tied to sensors and actuators. And in Lattice, we basically split this into 3 categories, like sensing, processing, and communication. And in sensing, we can collect raw data information like the pressure, temperatures, or location, etc. And this raw data information will pass to a processing part and doing some pre-processing work like encryption, DSP, and data filtering. And this information will pass to the local network or the back-end server on the net. So on the diagram on the right, it shows how Lattice tackled these problems in each categories. So on both ends, in the Lattice IoT platform, we will provide a list of APIs, a software description APIs for the I/Os and peripheral devices, while for the processing part, we use a RISC V processor plus the hardware accelerators. Today's presentation, we will just focusing on how does the processing part works. And how do we use the RISC V processor plus the leg-up generated hardware together? So basically, here's the basic user flow we need to do is first we identify the critical hotspot in a C program, then we pass this C program to the leg-up high-level synthesis tools and generate them in the FPGA while we have the remaining C program execute in the RISC V processor. And we hope the final hybrid solution will still maintain a low power and gain a high throughput. Next, I will talk a little bit about how do we use the RISC V and what does the architecture looks like in our product. So this diagram here shows the overall architecture of a RISC V processor and the leg-up generated accelerators. So in our platform now, we can allow the user to create a RISC V processor plus multiple leg-up generated accelerators. And our tools will partition the memory based on the size of the applications and the numbers of the accelerators. And one key thing I want to point out is if you see this memory architecture here, so you see there's dedicated memories for the processor and the dedicated memories for the accelerators. So our tools will detect whether the data memory is going to be used by the processor only or the accelerators only. We only put the data into the shared data memory when we realize the RISC V and the accelerator need to access the same memory. And the benefit of doing this is we can have the RISC V processor and the accelerators to run parallel. And this chart here, this diagram here shows you the give you a basic idea how does our processor look like in Lattice. So in Lattice, we implement a 4-stage pipeline, size-optimized CPU core, which implements the RISC-V IMC instruction set based on the latest specification. And we also have some optional features like interrupts or stores from the external I/Os and peripherals. We can allow the customer to create custom instructions for the accelerators, and etc. And this can be all configured through the Verilux parameters. And this slide shows you some benchmark result against the RISC-V processor and our Lattice legacy processor and some other processor from a third party. So we compared the DMIPS, the area, and code densities. And we normalized the code density to the RISC-V So if you look at the first column, the RISC-V and the fifth column with our Lattice micro-32i, you can see the RISC-V is beating our processor in all areas. And also, if you look at compare the second column, the RV32IM, with other processors, we benchmark. Looks really competitive and promising. So that's why when we first start this project, we picked RISC V in our initiative. So next, I will pass the presentation to Andrew.
Can everyone hear me okay? Hello? Okay, great. Thanks, Cam. So now I'll talk a little bit more about the leg-up high-level synthesis tool, kind of the design flow we're envisioning, and some benchmark results. So leg-up is a high-level synthesis tool that takes a C software implementation of your program and then compiles that into an equivalent Verilog RTL implementation. So it's similar in a way to BlueSpec and Vivado high-level synthesis, except we take C as kind of the design input. So this was developed from University of Toronto for about the last 7 years. I was doing this for my PhD. And actually, I'd encourage you, if you're interested in high-level synthesis at all, you could go to legup.org and download an open source version of this compiler. Doesn't include some of the latest features, but you can check that out. So the question is, what's kind of the benefit of doing this? Well, when we consider most of the users who are using kind of a typical ARM microcontroller or who might want to use this kind of lattice device, they're probably much more familiar with designing in C. Not a lot of engineers know how to do very low-level RTL design, and it can also be very painful to debug at kind of the RTL level. So we really want to kind of give a software user access to some of the parallelism that you can have access to inside the FPGA hardware, while still being able to describe their algorithm in C. It's also much faster to kind of debug and run test benches in C versus doing model simulations. And we can also do some design space exploration, so they can tweak some knobs on the tools if they want to target a higher Fmax or kind of get lower area. So kind of the vision behind this kind of design flow that we're talking about is the user would first of all describe their algorithm in C and use a kind of the normal C compiler targeting the processor, in this case a RISC V. In the past we had leg-up targeting an ARM processor and also kind of a MIPS processor. So in this case this is a RISC V that's been implemented on the FPGA, and kind of they're going to run that, profile that processor, their application, get some insight into where kind of the critical hotspots are. And then the idea is they'll take some segments of their original program, feed it into this leg-up high-level synthesis tool, and then what we'll do is kind of this push-button flow will generate an entire system where we have the RISC V connected to these automatically generated hardware accelerators. We kind of generate a bus, kind of memory architecture, and this all compiles onto the FPGA. And kind of the idea here is ideally they wouldn't have to touch any kind of low-level Verilog RTL code. And so leg-up comprises kind of the C compiler and this high-level synthesis program, and it's all written in based on the LLVM open source compiler. So just to dive into a little bit more detail of how this would look, if we just look at a very simple example here, we're performing kind of a multiply accumulate dot product operation in our C program. So what the user would do is they would identify at the kind of a function granularity what function they want to accelerate. They would pass kind of a tickle constraint to our tool, telling it they'd like to accelerate, in this case, this dot product function. And what leg-up will do is it will, again, look at this C function, analyze it, and build kind of a highly pipelined hardware data path that implements that function. So in this case, that loop would be completing kind of every clock cycle, doing multiple loads, the multiply and the accumulate all kind of in parallel. And then what leg-up will also do, so it'll generate that kind of Verilog module. It will also automatically generate kind of this memory map kind of wrapper function. So there's a bunch of code here, but basically at the top, it's kind of assigned some memory mapped registers inside the accelerator so that we can pass kind of a pointer to these arrays A and B that we want to perform the dot product on, can pass kind of a bound for the loop, And then what we can do is, again, these are storing the arguments across a bus to the accelerator. We can start the accelerator. And in this particular example, we assume kind of the processor is stalled while this accelerator is running. But as Cam mentioned, we also want to support this accelerator running in parallel. And again, this kind of automatically generates kind of transparently to the user. And LegUp will take that original function, kind of replace it with a call to this wrapper function that I just described. And this entire program now gets passed into the typical kind of software compiler GCC flow for the RISC V. And that will just run on the RISC V. So if we kind of look back to this architecture diagram Cam had showed previously, we now have kind of that dot product accelerator sitting attached to this bus to a RISC V. And we also kind of statically partition up some of our memory. So ideally, we have kind of a block RAM kind of sitting attached to that bus so that we're not kind of conflicting on main processor memory here. So kind of just to summarize, we start with the C program. We do this profiling and partitioning step. We run it through this RISC V tool chain. And again, we generate this entire system with a RISC V connected to the hardware accelerators. And then the user kind of will give them kind of an emulation or simulation view of that system to kind of get an idea of how much speed up they achieved. And then the example, this is supposed to be kind of an iterative process where they kind of keep tweaking their design, kind of like you do on a GPU where you're just offloading more and more computation into the fabric. So if we just look at, again, another simple example here, again, we're kind of doing a similar kind of dot product operation here. We're looping over these samples and kind of doing a sum of squares. If we run this on the RISC V processor that Cam discussed earlier, which has DMIPS of 1.64, each iteration is going to take about 6 cycles. We have to do kind of a load, incrementing the address, multiply, add, we're doing a branch. So to contrast with this, LegUp generates kind of a complete pipeline that exploits all kind of the instruction level parallelism available in this loop. So each iteration of the loop is completing in 1 clock cycle. So in this original case, we're taking about 6 clock cycles per iteration, whereas LegUp's taking about 1 cycle per iteration, so we get kind of a 5.4x speed up here. So this is a very simple example. You might be thinking we might be able to do this with just kind of a multiply accumulate instruction or something like that, a DSP instruction. But you could imagine this loop can actually get quite a bit more complicated. So you can really generate quite a complicated pipeline that can, again, be starting 1 iteration every single clock cycle and just taking advantage of the parallelism inside the FPGA hardware. So I'll just talk briefly about some benchmarking results that we looked at. So the first thing that we looked into, again, we wanted to look at some kind of image filtering, audio filtering applications, like edge detection, Bayer filtering for like an image sensor, some audio filtering applications. And what we want to do is implement these kind of by hand in RTL, and then also have a C implementation and kind of see what LegUp could generate and how close it was to a handwritten RTL. So to get a feel for how these benchmarks, we call these kind of streaming benchmarks. In this case, you might have an image sensor kind of streaming 1 pixel per cycle into this module that we've created, this edge detector in this example, and kind of that streaming back out, again, a 1 pixel per cycle. And we typically have some kind of constraint here that we have to meet to kind of receive all the input pixels. So we describe kind of this edge detector in C. So when we took an average across kind of 9 of these streaming benchmarks, in this case, we were targeting a ECP3, kind of a larger FPGA from Lattice. So I've shown kind of the averages here. So the first thing I want to point out is kind of, so this column here is kind of handwritten RTL. And then this is a ratio comparing kind of the LegUp generated circuit to the handwritten RTL. So first thing I'll point out is just in terms of clock cycles, the leg-up generated circuit was able to meet kind of that 1 pixel per clock cycle constraint we had for these streaming applications, or 1 kind of audio sample per cycle. In terms of Fmax, we're about 25% lower than something you'd write by hand. And time here, I've defined that as cycles multiplied by clock period. So we're about 30% slower than kind of a handwritten design. And our area was about between 8 and 18% higher than something you write by hand. But we still think this is pretty promising because we really don't want the end user to have to write kind of a low-level RTL implementation. So kind of we think this is promising. So the next thing I'll just show is very recently we kind of got this whole flow working. So it's a push-button flow where we can take an application, kind of take the, in this case, for these benchmarks, the most compute-intensive function, and kind of mark that to leg up to create an accelerator for that function and kind of see what type of speed up we'll get out of it, kind of just using the push-button flow. So we have different benchmarks here, some smaller ones like a FIR filter, and also some kind of encryption and kind of video and audio kind of encoding applications. So what we found was we're anywhere from kind of 2 to like about 5x faster than just running on this RISC V alone. So kind of, if we take an average, we're about 3x faster on average by kind of accelerating a compute-intensive portion of this benchmark. But a little bit of the problem we're noticing here is for some of these larger benchmarks, the accelerator that gets created can't really fit inside this very small FPGA that we'd like to target. It's only about 4,000 or 5,000 LUTs. So for instance, this SHA benchmark, if I remember correctly, took about 6,000 LUTs alone. So really, I think where this makes the most sense for generating this accelerator is thinking of this accelerator more like a coprocessor, where it's kind of sitting attached to this bus, hopefully connected to some kind of external IOs, where it can process data independently of the central RISC V processor. And basically, as Cam mentioned earlier, that accelerator, we can statically identify kind of memory that the accelerator is using exclusively and kind of create those blockgrams so on the FPGA so the accelerator can access them and kind of run it as a coprocessor. The other thing that we're investigating right now, again, to make sure that we save as much area as we can for this small FPGA is kind of the current architecture. We're assuming we take a large chunk of C code, turn that into kind of this coprocessor accelerator. Instead, the user might want to kind of do a more lightweight approach where they want to add some specific kind of DSP or maybe encryption custom instructions based on their application. So the idea here is we could mark kind of create those kind of custom instructions, so very small functions, and then kind of tightly couple that accelerator to the RISC V. And we get much more area efficient designs here because we can share that custom instruction across many places in our application. So that's a work in progress, and thank you very much. That's all for now. Yeah.
Thanks, Andrew. Thanks, Cam. We'll have more than a few questions, I think.
Hi, Greg Sullivan, Draper. I was just curious about one of the early slides in this half of the presentation. It looked like you had the CPU core on the FPGA also?
Yeah, that's correct. Right now, we've implemented...
I'm assuming that's just convenient for you. I mean, are you envisioning a ASIC CPU core tightly coupled to an FPGA fabric where you use the FPGA specifically for the acceleration?
Yeah, exactly. That's a great question. And I guess maybe even Cam could speak more on this, but we are thinking, for now, we have this kind of RISC V implementation on the FPGA. But again, the resources on that FPGA are very limited. So I think long-term, it would be better if that RISC V was actually kind of hardened into an ASIC, maybe on the same chip as the FPGA or something like that, connected to the FPGA. It kind of just depends, I guess, what Lattice wants to do. I don't think it's known for sure what direction they're going to take. But I think it would make sense to harden it.
How does this work with like Okay, Guy Cohen from Mellanox. So maybe a few questions. One is that totally asynchronous to the processor pipeline? And second, how does it work with memory management? If you have
So
memory
yeah, that's a
management.
great question. Question is kind of, is it working kind of asynchronously from the processor, and kind of how do we deal with the memory issues? So so actually, I think that's one of the pieces that we still need to work on, kind of how do you synchronize the memory between kind of this accelerator and the processor. So right now we're kind of pushing it more onto the user to kind of make sure that they're not kind of accessing the same memory, so kind of partitioning the memory space into different regions. In LegUp, we actually do have some facilities to use kind of a p-threads approach where we could support kind of some mutexes and locks to, again, that's kind of passing it towards the user that they'll have to kind of have this region of memory that they kind of lock or mutex. And in terms of the other question, yeah, ideally the processor would be running in kind of in parallel with the accelerator, but then you do have these kind of memory issues cropping up.
Hi, Steve Milburn from Draper. So if you have a function that you want to accelerate that is more complex than what you can do in one clock cycle of your current frequency, does your synthesis engine end up splitting that instruction out to pipeline it up to take more than one clock cycle per iteration of the loop, or do you end up slowing down your maximum frequency to whatever the lowest common denominator of whatever functions you've accelerated?
Yeah, that's a good question. So typically, so LegUp kind of statically tries to kind of analyze that loop and kind of get it so that it's starting one new iteration every single clock cycle. There are some cases where you can't do that. For instance, if you have kind of dependencies across loop iterations. I don't think we've seen cases where kind of an operation needs to take more than one clock cycle. Typically, like an operation like a simple kind of add, we're dealing with kind of RISC style operations here. They can complete in one clock cycle. And typically, kind of that pipeline could get quite deep if like the body of your loop was more complicated. But yeah, typically, we don't typically deal with operations that last more than one clock cycle, no.
Drew Taussig from Synopsys. It sounds like a lot, Andrew, like your tools is high-level synthesis. Can you expand a little bit about how it's different, how this is maybe something better than just standard HLS kind of flow?
Yeah, it's a good question. So kind of how is this different than some of the other HLS tools out there? I would say it's in many ways quite similar to the other HLS tools out there. I think we have some interesting ideas where, like I mentioned, we kind of have this p-threads way of describing kind of a parallel program, which I haven't really seen other tools using. But really kind of our vision here is to target kind of a software engineer, so make it much easier for kind of an embedded software engineer who's maybe used to programming just a typical ARM microcontroller, make it easier for them to take advantage of some of the hardware. A lot of some of the other high-level synthesis tools, it really seems like you would need quite low-level knowledge of kind of, you almost would have to be a hardware engineer to kind of use the tool, kind of understand it. So again, we're quite similar, but the kind of vision is to make it simpler for microcontroller users. That's kind of the angle we're going here.
Rishi or Nikhil from BlueSpec. So first question is, do you have an overhead in copying data, argument, and result arrays, for example, between your partition memories between the host and the CPU? So that was one question. The other one was, what if I have two outer level loops that are both acceleratable? Can you do those concurrently, or do they go one at a time?
That's a good question. So in terms of the first question, kind of passing data around from the kind of processor to the accelerator, mostly what we've done to kind of deal with that situation right now is kind of, like in that function I showed, we're kind of passing a pointer over to that accelerator. And then the idea is that system generator is smart enough to ideally partition up your memory so that that pointer, when it accesses the bus, kind of goes to that separate block RAM that's sitting on the bus. So ideally, we try not to transfer a whole bunch of data kind of across over to the accelerator. But in some cases, you kind of have to. We're thinking about maybe using kind of a simple, lightweight DMA to maybe do that in the background. in terms of your other question, oh yeah, the two kind of loops. That case, we don't really support that right now. I guess those two loops would have to be flattened into one. It's sometimes in the compiler, in the LLVM compiler, it can kind of flatten those into kind of one loop. In that case, we would support it, or just the inner loop would kind of be parallelized. The outer loop would, again, kind of maybe rerunning on the processor. Yeah, that's maybe one area that we need to focus on. Thanks.
Thank you, Andrew. Very interesting.